My name is Janelle Kerr. I am the Director of Minerals Geoscience at the Geological Survey of Queensland. Thank you for coming along to the most recent webinar in our series. We have a great set of talks today. I'm really excited to see them. So I hope you can join us for the full set of presentations. Before we get going today, I'd like to start with an acknowledgement that I am joining you from the lands of the Turrbal and Jagera people here in Brisbane, or Meanjin. So I'm sitting on traditional lands with traditional custodians, and I'd like to acknowledge their continuing connection to country, the value that they bring to our society, and their role going forward as a nation. So I pay my respects to their elders past and present. So today we have a series of talks from the people in our minerals geoscience team, but before I let them take it away, I'm going to do a shameless plug about some upcoming and current things that are going on in the GSQ. So we have just opened a new grants program. So people are right this moment able to apply for a new style of grant offered by the Queensland government. It's to help exploration companies and mining companies and other people in the resources sector look for critical minerals in mine waste associated materials. So we are taking applications now, and we don't run this as a round. It will be applications until the allocated money is exhausted. So jump on, have a look through the guidelines. If you've got any questions, we've got a contact email there. That'll go straight through to our grants team. They'll be able to answer any questions you might have. The other shameless plug is for an event that we have coming up. So we're going to be taking our regional seminar to Mount Isa this year. We do a regional conference each year. So this year is Mount Isa's turn. We will be up in Mount Isa on the 21st and 22nd of August, showcasing all the work that the GSQ and its collaborators are doing. So I hope you put a save the date in your calendar, and you can register to get updates through that QR code on the screen. All right, that's enough shameless self-promotion. So I am going to pass over to Vladimir Lisitsin to introduce the work that his team is doing and give you a bit of an overview of what's going on in today's webinar. Over to you, Vlad.
Hey, thank you, Janelle. Good afternoon, and thank you all for everybody to join us here today. So I will introduce a GSQ work program aiming to characterize signatures and footprints of deposits across Queensland. That's pretty much the subject of this entire webinar. And I will take you through the logic and the workflow of the program undertaken by the very dedicated and capable mineral systems team and our collaborators across the universities and industry, and I'm presenting on their behalf. So in this webinar, I will give a brief introduction of the logic, so why we're doing it, what is the purpose of this entire program, and we'll give you a few illustrations of how to take deposit scale information and expand beyond deposits, get out of deposits, do inter-deposit comparisons within the district to province, so stepping out from deposit to regional scale. And after that, Elena will, in the next presentation, will go the opposite way in terms of spatial scale. So she'll be going from the scale of deposit and drill cores from tens to hundreds of meters to tens of centimeters and to the micron scale. And she'll introduce a great deal and variety of our microanalytical work, which we're increasingly doing in the GSQ. And after that, Alkis will take us in more detail through the logic of mapping out a key mineral system from inside out, from ore to distal footprints. So that's pretty much the ultimate goal of from ore signatures to distal system footprints of the entire program. And Al-Tamini and Rhiannon will show examples of individual deposit scale case studies, 2 out of about 70 plus, which we attempted to characterize over the past 4 to 5 years. Okay, so after this very long introduction, let's get into that. And first of all, let's talk about why we're doing this work. So why have we spent so much effort, so much resources to characterize signatures and footprints of known deposits? After all, they're known. And why the results we produce should matter to you out there, and particularly out there in the industry, because our main focus is to provide data sets and information which can be useful, particularly for exploration industry. And we're trying to address two main exploration challenges in Queensland in particular, but the challenges are relatively universal. First is defining deposit signatures, what's in the ore, what's in the proximal alteration, for the purpose of discrimination between different deposit types, deposit and mineral system types, and to assess critical mineral endowment and potential of different deposits types and styles. And second, try to build up multi-property database, dataset, and useful information and templates to allow people to be more confident navigating through distal footprints of deposits. So how to find your way around in non-mineralized rocks through obvious or subtle, weak or strong alteration. And in particular, in the past few years, as part of this program, we became particularly focused on characterization of critical minerals in ores. And that's one of the reasons of the wide variety of geochemical techniques, geochemical methods we're using to analyze ores. And this information was pretty sparse for Queensland deposits, including the major ones at the time when we started this program just 4 years ago. And the foundation of the mineral system characterization work, all of it is sourcing and sampling multiple representative drill cores through key deposits and their footprints. And one of the key outputs of this program is to make this rock collection of drill cores and individual samples accessible and usable to external users, including industry and researchers. So for each individual deposit, we're trying to use a consistent sampling strategy. So focusing generally on sparse sampling from 2 or more representative drill cores intersecting a deposit and its footprints. Trying to capture spatial variability of mineralization and alteration, and hence we're aiming to do at least 30, preferably 60, sometimes more than 100 samples per deposit. And for select large deposits, like the example shown here on screen, we're trying to step out way outside the ore shells, way outside the proximal alteration, and step out as far as we can go, try and characterize distal footprints and distinguish distal footprints of a deposit from regional background and distal footprints of a mineral system. And the general approach is to go inside out, more extensive sampling in the ore body and across its 3D shape, and stepping out and getting sparse up. So this is both by design, because internal variability of ore in proximal alteration is largest within and close to the deposits, and for practical reasons, because samples are much more readily available inside the deposit than a set distance away from it. So the general approach, try and characterize everything within, and then stepping out outside and see how far we can go. So far to date, over the past 4 years, we have covered a great deal of ground across North Queensland, Northwest, Northeast. We have covered more than 70 primary deposits, and by now many dozen secondary deposits through University of Queensland. We're consistently doing continuous core scanning, multi-element geochemistry, and detailed microanalytical techniques. And for now, the focus was on northeast Queensland because they are number 1 and number 2 mineral provinces and mining districts in the state. But the aim is to expand through the entire Queensland and cover every mineral system type of note and every deposit type of note. So there is still a fair way to go. So a quick illustration of the general workflow. I'm not going to dwell on that too much. I want to reiterate again that first and foremost, we need to work on well-characterized, abundant samples of good quality. And that was the major focus of the first 2 or 3 years of this program, and it's still ongoing. We're still on the hunt to find and retain for public use representative drill cores through all key deposits and the alteration types. And through the best of the drill cores, we're taking them through continuous scanning. So the usual routine is everything we can goes through our in-house high logger for spectral mineralogy, and a subset of the best drill cores goes for continuous XRF scanning, TrueScan Mineralizer. We started employing petrophysics recently, and so we're using the results of continuous core scanning to make more intelligent choices about our spot samples, which are 30-50 centimeters, on which all the rest of the work is getting done. Multi-element geochemistry for just about every element of any interest to just about anybody in the industry and in general public. We're going through micro XRF, TIMA mineralogy, increasingly getting into mineral chemistry, and isotope geochemistry, including geochronology. And here at the bottom right of the screen, I'm just showing a couple of examples of isotope geochemistry. Here just for copper, iron, and oxygen. But this is a shorthand for the entire variety of isotope geochemistry we're doing, and we're doing a fair bit of uranium, lead, argon, renewable osmium geochronology, and multiple other isotopes that I'm not going to dwell on that here. So shown here is an example of the general logic and workflow of how the work was organized, going from region to actual deposit scale data acquisition. We're focusing on the region, we're identifying key mineral system types, and we're going in each major mineral system, top down from largest to less significant deposits, aiming to cover everything economically significant to date, everything potentially economically significant in the future, and to characterize natural geological variability of different members of a particular mineral system family. And in this case, I'm not going to talk about anything but IOCG family, just for the brevity, and again, just to illustrate the workflow and what kinds of information and why we're doing it. And the diverse IOCG family in Cloncurry district, that was a particularly good example to illustrate the workflow, just because its variability, just because deposits of this family are so much unlike each other. So it's very good to illustrate why it's important to collect internally consistent data sets, and why it matters to do inter-deposit comparisons for different deposits within the same family. So I will show just a few illustrations and focusing pretty much entirely on whole rock geochemistry as the data type the closest to the industry, and the other presentations will focus on more advanced microanalytical techniques. So first, the most intuitive way probably to illustrate multi-element geochemistry, geochemical signatures of different deposits. It's by relative enrichment compared to average crustal abundance. And shown here are 5 pretty much end members of the IOCG family in this district. The main point here is to illustrate that there is an overall similarity, so we can identify similar signatures of enriched tellurium, copper, selenium, as the main common factor of all IOCGs, but beyond that, there is much more variability than similarity. And using the geochemistry of 67 elements we're collecting, we can assess critical mineral enrichment, and there are several critical minerals which are of a particular significance in IOCGs, and rhenium in particular sometimes get to extreme enrichment, sometimes in some deposits get into concentrations where rhenium can be considered the primary commodity, which is pretty unique and unusual. Another way to compare and discriminate geochemical variants of IOCGs, focusing on ore elements, the elements significantly enriched in at least some IOCG deposits. And here, after applying several relatively standard data processing techniques, we can easily visualize three geochemical variants of IOCG deposits in the district: Ernest Henry and the likes, which is the most known, gets much more attention than the others, and probably the rarest of the geochemical kind. The group in blue has less extensive multi-element geochemical signature, but still relatively complex. And in the red and blues lie most of the economic deposits mined to date. And the blue group includes iron sulfide copper golds and so-called ironstone hosted deposits. And the third group has the simplest geochemical signature with the smallest number of elements enriched, and that's the rest of IOCG deposits in the region. And this is an illustration of how multi-element geochemical information can be used for easy discrimination, easy screening of any samples from any IOCG-like prospects occurrences in the region. Just to give a quick assessment of what kind of IOCGs, if any, it feels and looks more like, and some explorers in the industry are already using this for such purposes. And you can use geochemistry for other deposit types and mineral systems for this or different data uses. Another illustration of the use of multi-element geochemistry for IOCGs in particular is to highlight geochemical variants in terms of alkali-calcic and ferric metasomatism. Here also the main purpose is to illustrate that Ernest Henry in red has a alkali-calcic and ferric signature of alteration significantly different from just about everything else. And the vast majority of IOCG deposits in the district have low to moderate potassium, calcic or high iron, calcic, ferric, and sodic alteration. And our fresh off the press geochemistry for Rocklands. Rhiannon is going to show it in more detail in this diagram, and it's also one part of that ferric rich calcic ferric to sodic alteration. And in terms of assessing critical mineral potential of different variants of IOCGs, cobalt is particularly consistent. IOCG deposits are not born the same. Some are much more enriched and potentially productive than others. And so we can focus on some potentially geochemically interesting parts of deposits and samples, and investigate further ore mineralogy, for asking questions like the deportment of cobalt, the modes of occurrence of cobalt, which has major implications for metallurgical purposes. And Rhiannon will take you through some more details. These are examples from Rocklands. We have started our work in Northwest Queensland. That's where we spent probably last 6 years. Northeast Queensland, we started a bit later. And this is a particularly complex region with multitudes of very different mineral systems and deposit types of different ages, sometimes in overlapping regions, sometimes multiple mineral system types present in the same deposit, which adds complexity and highlights even more significance of using microanalytical techniques. And we have started to work from intrusion-related rare metals, Grison, porphyry, vein, and scan tin tungsten moly deposits. But we have had a closer look at gallium and bauxite, and now we're going through extensive work on intrusion-related gold and epithermal gold. That's something still ongoing, something which we still have about 8 months to go. And finally, from deposit signatures to footprints, So that's the ultimate purpose number 2, and in the industry probably it's the most significant purpose and use of these data sets and results we're producing, trying to make navigation through distal footprints of deposits much more effective and easier. So what we're trying to do is to create templates, to create reference data sets where we can map out and identify recognition criteria for proximal to sometimes intermediate and distal deposits to mineral system footprints. Illustrated here is what we already can do in bulk geochemistry mineralogy. We can easily recognize mineralization. We can easily see proximal alteration full of K-spar in the proximity of Ernest Henry. It's getting trickier when we get beyond 1 kilometer. So we can have some assumptions, but we're not sure. And beyond that, all analytical techniques probably reach the end of their usefulness. And that's where we're entirely within the realm of microanalytics, and Alkis will take you through there in more detail. So for now, we have released a fair bit of information, mostly as data sets already, starting from precursor reports, which were released several years ago. And we're releasing data sets as soon as they're ready so that external users can start using the data before we are done with our interpretations. So some of the data sets fresh off the press and not so easy to find. Continuous XRF data through Mineralogical, well, done by Mineralize, is accessible from Mineralogical, and there are several data sets which have been released quite recently. And we're certainly trying to engage pretty strongly and regularly with the industry. So we have had several interactions. Well, we had several interactions last year, and I will repeat whatever Janelle already advertised. Please join us in the technical roadshow, the workshop in Mount Isa in August, and that's where we're going to showcase the vast majority of the data which we produced over the past 4 to 6 years. And a particular thanks to all the industry participants of our collaborative effort. Without their help, our work would not be possible. So shown here are just the most active contributors, and we're certainly welcoming other companies to join in and to work with us, because I sincerely hope that this kind of work is not going to be stopped. We're going to continue. I shall leave it here. Thank you.
Thanks very much, Vlad. Pretty well on time as well. So we don't have any questions at the moment, so we might just go on to the next presenter. A quick reminder, you can ask questions at any time during this webinar through the Q&A function, which is at the bottom of your screen. We will have a Q&A session at the end of this series of talks. So if your question doesn't get answered on the way, we'll have some time at the end. Are you able to stop sharing that?
Okay, trying to find it.
Yeah, no worries. So our next speaker is Elena, and she is obviously from Vlad's team as well, and she'll be talking us through mineral deposit characterization workflow, building on Vlad's talk already. Thank you, Elena.
Yeah, I'm trying to find the right screen to share.
All good?
Just let me know if you see the right screen and if you can hear me.
Perfect. We can hear and see everything. Looks
wonderful.
good.
So I can start. So Vlad's presentation nicely set up the scene for the scope of our work as GSQ, as well as showed us a range of deposit types that we are to deal with across the state. So in my presentation, I'm going to focus on the workflow in our process of deposit characterization. If I can move to next slide somehow. Excellent. So this is a very just solid summary of our workflow, and you can see we're certainly starting our characterization process with the core scanning. And here it's very important that we have representative core selected, the core which characterize the best, the most important part of the deposits, or some discrete ore bodies. So, and that's always, it's not always possible. And if we have the luxury of choose the best representative drill cores, that's what we do. And Vlad already highlighted the core scanning techniques we are using, so I'm not going to dwell too long on this section, but we'll talk on individual techniques a bit further. So our next big step is the collection of multi-element whole rock geochemistry data. So this is a quite important step because it's costly and it provides us with the information needed for our characterization. So the previous step, it's quite important preparation step to make sure we did the right sampling for the whole rock geochemistry. And the last one, not the least one, is our work on the microanalytical end of the characterization process. So before I move on to the individual steps I highlighted here, I would like to emphasize that this workflow is designed so we consistently apply this across different deposit types and across our their geographic location to make sure we produce systematic and comparable data sets across the state. Next one. So this is the example of the data we're collecting using our high-logger instrument, and we are really lucky to have this instrument available at EDC, so we can use it as our initial step during the characterization process. And this is a very spectacular example of the drill core from Rocklands. And again, Rhiannon will be talking more specifically about these deposits later on today. But I would like just to emphasize that this sort of data allow us to visualize and understand the different lithological domaining in the down the hole, which is very nicely emphasized by different mineralogy or the mineralogical paragenesis. So here we can clearly see distinctive carbonate or garnet-rich zones, and also different style of alteration, albite, actinolite, Cape feldspar. If we compare this data set with the data we collected on the same drill core using the mineralized instrument, you can see we have quite a satisfying consistency between two data sets. So high-logger data on the top and the major element distribution using the mineralizer data, where we can see quite nice distinct characteristic in terms of titanium zirconium ratios and distribution of silica and iron across, which is quite nicely consistent with the domains observed in a high-logger, and also consistent with our visual observation during the core logging. So this also, the mineralizer is also a very nice tool just to highlight our main ore bodies where the mineralization occur. Of course, it could be, it's nice when we can see it in a hand specimen, and we combine this information and compare with the data which are commonly provided as an analytical assay by our industry partners. So this all information provides us quite a good confidence in the selection of the samples that we are using for our multi-element geochemistry. And this is important because this gives us this essential fingerprinting of the very different or mineralized systems. And here Vlad spent a lot of time looking at this kind of plots, but I would like just to emphasize that we are using a different set of methods. The ones that are commonly used by exploration industry, so they can have a direct comparison, but we also apply quite more advanced, more expensive analytical method just to make sure we can produce this detailed understanding of the concentration of a wide range of trace elements. And also, as Vlad mentioned, critical metals are also in a big scope in this characterization process. So now we are staying at the stage where we can have quite good information on the concentration of these elements which are or related or critical metals, economically important metals and elements. So, but the question is how they distributed in the rocks. Are they associated with a specific ore minerals or any other rock forming minerals? It's still a big question. So here where our microanalytical work is coming into play. So so here I will focus the rest of my talk on what microanalytical work we are doing during our characterization process. And I'm very happy to say that recently installed Bruker Tornado instrument was a great success. So it was installed at EDC in July last year, and Al-Tamini and Alkis are super users who mastered the usage of the instrument and data reduction. And this image is actually taken during the first day of the instrument installation. So what is instrument capable of? So we are using the instrument for the spot analysis during daytime when we do our active sampling. So we can resolve ongoing question on a way where we're sampling. While over the night, the instrument working hard to produce us this kind of mapping. Where we can scan the areas up to 16 by 19 centimeters in dimension to receive these details maps of the distribution of the range of the elements of our choice. So this is the example for the Pegman zinc lead deposit. And another example is tornado mapping done for the Rocklands, again as an example. So one of the maps showed distribution of sulfur, copper, and cobalt, and the other map shows the mineral phase map. This is the processing using the AMIX software. So we have quite a nice understanding of the mineralogy and the elemental distribution. However, if you look at this map, the cobalt is still, it's interesting. We see some quite dense places where the blue cobalt concentration much higher. However, with this technique, we could not resolve its particular mineral association. So again, this is where we zoom in with our TIMA work. Before I go to the TIMA work, I would like to say that we also are using the Maya mapper in collaboration with CSIRO. And this is we do for larger samples, which have the samples which have particular complex and fine structure. So we can, the Maya instrument have a much higher intensity of X-ray intensity and better resolution, so we can do mapping, a very detailed mapping of our samples. And this is one of our favorite sample, the map done on the sample from Mount Isa zinc lead deposit. So now we can step it to our further zoom in working with the TIMA instrument. Well, my favorite topic, try to stop me here. Well, the TIMA is a TESCAM integrated mineral analyzer, which enable us to produce the mineral abundances map, element distribution maps, and also provide this information on the textural elements. So we do a lot of this work in collaboration with others parties. We send some samples for to AXT, and we also collaborate with Kerr, who help us to get through the volume of the samples we have. However, a lot of data we collect ourselves at the QET labs, CAF labs. So special thanks to the staff for training our GSQ staff and providing all the support in this work. So at QET, we do quite a high resolution mapping using the TIMA instrument. So we use the dot mapping option, and you can see we're using 2 micron pixel size and the 6 micron dot spacing. It takes quite significant time to collect the images for the standard 25 micron millimeters mount, and even longer for thin section. So in next few slides, I try to show you an example why we bother to spend this efforts in time to collect this detailed information. A spectacular example of the thin section from the pegment deposits. So here I just wanted to show you what kind of maps we can produce. It's backscattered maps, very high resolution, that we can produce element maps, and we can choose our own set of elements or do it for individual element. And certainly very important to have the mineral phase mapping available. So here for the pegment deposit, we can see it's basically the major phase is a granular garnet with the bending this interstitial grains of this sphalerite in purple and apatite in this case. Well, very nice software capacity of the TIMA where we can produce maps for individual mineral phases. And it's really handy when we are working with numerous collaborators who are focusing their research for specific minerals or specific analytical technique, in situ technique, trace element analysis, or isotopic analysis, where we can provide them with sample and these details map for the very specific and clear targeting. Another example of our TIMA mapping is resolving our paragenetic sequences. And if we look at this TIMA image, which I borrow from our PhD student, Michelle Moxie, who is doing her project on one of our deposits from Northwest Queensland, just to illustrate that we have this pervasive albitization, totally overprinting the original mafic porphyry, original rock fabric, with the later cross-cutting alteration, which is clearly shown in this hot pink color, potassic alteration, and the very latest cross-cutting and manifested by this blue color for carbonates and quartz. So another example how we can use this TIMA imaging and in combination with the observation on the core and hand specimen to just improve our mineral paragenetic relationship in the variety of the deposits. Another example is just using TIMA technique to define and look at the distribution of minor accessory minerals and also critical metals. So in this case, we are looking at Mount Isa copper style deposits where we know we have concentrations of cobalt well over 100%, sometimes several thousand ppm of cobalt. So when we look in details, cobalt is known to associate with pyrite and be just accepted in a lattice. But in this case, we can clearly see that cobalt form in discrete sulfide all minerals, and this is an example of lineite in bright blue. So this sort of information, it could be very important for the cobalt extraction and recovery processes. Another example, when we do a lot of work, we started to do a lot of work targeting apatite to characterize trace element compositions, and also use it for geochronology in this in situ analysis. And here's the example when it's quite straightforward. Huge grains of apatite associated with this bending of the carbonates and quartz, and some of the sulfide, pyrite, and the arsenopyrite in this case. In contrast, some apatites are much more trickier to find, and most importantly, in this case, we have clearly two generations of apatite. The apatite which is sitting within the host rock in the siltstone, and the ones grains which occur within this cross-cutting mineralization vein. So if you crush this rock and extract your apatites, the results for trace elements and particularly geochronology could be very confusing. So hopefully by doing this work, we have a perfect targeting of these apatites grains, and also our interpretation on the geochronology would be much better. And my last example of the TIMA imaging is the TIMA map produced by our collaborators at Curtin University, where we are targeting a range of sulfide for sulfur isotope analysis. And here's an example. We have two contrasting type of the veins, some solid large ones and some other veins which are cross-cutting, and they much thinner. Both of these have the same set of the sulfides, bornite, pyrite, and chalcopyrite. So we can, having this imaging, we can potentially discriminate different generations of these sulfides. So how we achieve this, all this microanalytical work? Yeah, we do best to cover a lot of work ourselves. However, with our multiply project and collaboration with the other institution and university, this wouldn't be possible. So a big acknowledgement to this project and collaborators. So we have very recently reported and produced the technical note and data release for our first set of microanalytical work. So the QR code is here to provide you with link if you would like to look at this set of data. And also, if you would like to look at our larger data set, including high logger data, whole rock geochemistry, there is a QR code to link to our previous data releases. So just at the end to say that we hope this pre-competitive data available on our GSQ open platform really help in the industry for more effective way for the exploration targeting. And certainly this work wouldn't be possible without the contribution of all our GSQ team, and some are listed here, and also our external collaborators. Thank you so much.
Thank you so much, Elena. And I would encourage everyone to go and read that microanalytics reports if that's something that's interesting to you. That is a huge amount of work. It's really great work by the team. So please do take the time to have a look at that. And the data is there as well if you want to go and dig into it in a lot more depth. So no questions at the moment, Elena, so you're off the hook on answering anything. Next up, we have Alkis, and Alkis is going to take us through a case study from Ernest Henry looking at distal footprints for mineral systems. Thanks very much, Alkis. Take it away. Oh, we lost your presentation. We don't have any sound for you at the moment either, Alkis. We can see the presentation, but we can't hear you yet.
All right, having some trouble with the audio here.
Okay.
But can you hear us now?
Yeah, we can hear you. You're all good.
Okay. All right. So I think I'll just feed the audio will be coming through Tamini's laptop. All right.
Not a worry. Thank you.
Okay. So thanks, Evan, Janelle, and Nick and Nathan for organising the webinar today. So we're talking about distal footprints, mineral systems, and particularly looking at the Ernest Henry IOCG deposit. So we look at basically a combination of mineralogy and geochemistry to understand how the footprints and fingerprints of the system change with distance to ore. So I want to thank everybody involved in the work as well. So they're listed here, but also our collaborators too. So a bit of rationale and aims. We want to build on existing multi-element geochemical data sets and use these to then identify the footprints in sparse data around the ore body. So to do this, we need to cross-validate the geochemistry and the mineralogy of alteration footprints. So we want to go inside out, so from known signatures of the ore deposit to the unknown. So we're really trying to test for a near-miss scenario here. And one of the themes of this talk, which will come up quite often, is that we need more than bulk geochemistry. So we need to constrain the mineral chemistry of suitable alteration phases so that we can differentiate between the background, alteration, and ore stages to identify the fingerprints of the mineral system. So as I mentioned before, we have a lot of collaborators. So particularly in this space, a lot of collaboration with QUT, UQ, Codes, JCU, ANU, CSIRO, and AXT. So most of us are pretty familiar with the Ernest Henry deposit, but I thought I'd give a brief background on the deposit itself. So it's in the eastern Mount Isa province, and it's hosted in the Proterozoic felsic intermediate metavolcanic rocks of the Mount Fort Constantine Formation. So these rocks were intruded by the Ernest Henry diorite around 1650 MA and later deformed and metamorphosed during the Eisen orogeny between 1600 and 1500 MA. So in the diagram on the left there, you can see the copper gold mineralization, which is occurring as a south-southeast steeply dipping breccia pipe, which is dominated by a magnetite pyrite calcite matrix with K feldspar altered clasts. So the matrix is so in the center of the breccia, it's more matrix supported, where you get your highest copper gold grades, and then some transitions to clast supported, and then crackle breccia towards the outside of the breccia. So the breccia pipe itself is bound by the footwall and hanging wall shear zones, and also the Marshall shear zone to the south. So a lot of work's been done on the alteration paragenesis at Ernest Henry. So broadly, there's an early regional sodic calcic alteration, which is overprinted by pre-ore potassium manganese iron and K feldspar alteration, followed by your copper gold mineralization, and then post-ore alteration and veining. So in the post-ore stage, the veining's likely, typically carbonates with some recrystallized sulfides, but also you do get alteration of chloride, of biotite to chloride, and of feldspars to cerussite too. So the images on the right there are some examples of these stages in drill core. So you can notice the brick red K feldspar alteration in the ore breccia, but in deeper parts of the system, you have these coarse veins of actinolite and carbonate sulfides. And then you also have some biotite and chloride alteration in those ones, but that's more prevalent in distal samples. So the image on the far right. So here's a geological map showing the distribution of the drill holes that we've sampled for the study. We have a relatively good spread from the north, not so much in the south. We just have that lone drill hole there, EHMT001, which hits the Ernest Henry diorite. Of course, we would love to get more samples and more drill core from around the areas we don't have samples, particularly to the east. So all the holes have been put through HiLogger, which Elena showed in some detail earlier. So we've collected over 500 samples. And from these, we've done about 230 samples of geochemistry. So the 3D model on the right shows the dip and breccia pipe with the drill hole traces and the location of the samples in 3D. So again, decent spread in terms of distance from the ore body to, I guess, the more distal holes. But this will allow us to then test how the footprints change with distance to the ore. So looking at some of the geochemistry of the ore, so Vlad showed a similar slide earlier for other IOCGs as well in the area. But just to revisit that the ore signatures at Ernie are pretty enriched in tellurium, rhenium, arsenic, moly, selenium, and other metals such as copper and gold, of course. So we want to know the differences between the ore signatures and the alteration signatures. So all these samples were analyzed had over about 0.1% copper. So moving on to the next slide, we can see this in comparison with other samples that are more typical of the alteration in the deposit. So the red here is, again, the ore. The orange is the copper and gold veining, so are proximal to the deposit. And the green is potassium, iron, and calcic alteration. Then you have your blue, which is your sodic calcic. So we can see that tellurium, rhenium, and selenium are quite elevated in all the alteration stages as relative to crustal abundances, relative to also the mineralization. So this might be due to anomalous levels in the actual host rocks themselves. So many of these enriched elements as well are typically present in sulfides, but we want to target non-sulfide alteration minerals. So a couple of good potential candidates in terms of geochemical indicators could be arsenic and manganese, which are all quite elevated and generally do also partition into common silicate minerals. So how does this look in 3D space? Again, Vlad showed us on the slide here. But basically to give an idea about it, the colors here obviously reflect the previous slide as well, where you had your mineralization and alteration stages. And the size of the circle here represents the copper grade. So here we can see that to the south of the deposit, you have more sodic calcic alteration, as well as in the very distal samples to the north. And we also have the potassic iron calcic trend just north of the deposit. However, this really just shows the limit of bulk rock geochemistry, as much of these trends may in fact be influenced by differences in the host rocks. So we do have variability from felsic to intermediate to mafic metavolcanics, as well as the Ernest Henry diorite in the south. So the important thing to note here is the presence of multiple stages of alteration minerals across this model. So we can see biotite, chlorite, and actinolite forming here I guess within the 1 kilometer radius of the deposit. As well as up to 3 kilometers in the in the yellow dashed box over here. But then biotite and chlorite still persist even in the more distal samples. So in order to target the right alteration, so we need to do this in order to target the right alteration phases to then identify reliable fingerprints of the mineral system. So this brings me to the characterization part of the study. So on the left, so these images are here taken by the Brooker microscale tornado, as Elena talked about previously. So on the left, you can see an example of the pre-ore stage, whereby you have biotite and magnetite alteration overprinted by a late carbonate and apatite vein. The middle image is of your typical matrix-supported breccia, and then 4 meters away from that is about some late carbonate veins with some likely remobilized sulfides. So these, again, were taken on the Microscale scanner, and we use this as a fundamental part of our workflow now to select samples for further microanalysis, such as for TEMA, which moves into the next slide. So this is some preliminary work that's been done by Shin and Renji from UQ and forms part of our ongoing collaborations in this space. So we want to differentiate between different ore stages and alteration stages. So the image here is from a sample of pre-ore K-felsic biotite and magnetite garnet alteration. And we can see that there's a lot of contemporaneous apatite grains within this alteration stage. So using laser ablation ICP-MS, we can then obtain these rare earth element fractionation patterns of apatite, in which case we have a middle rare earth element enrichment and a heavy rare earth element depletion. So this might be due to the presence of garnet, which might preferentially partition heavy rare earths in this case. So doing some uranium-lead dating on this puts this apatite in a reasonable age range for the pre-ore stage. However, a lot of this still needs to be validated and tested further. So another example of that is some apatite from the Sinor breccia. So this apatite is clearly in association with the sulfides and magnetite. However, the rare earth fractionation pattern is markedly different. So you see quite flat and also a negative European anomaly here. Going to the geochron as well, younger age, again, could be within error. So again, we need to do a lot of follow-up work on this, and Shin's working on another round of samples actually. And we also see some pretty interesting trends in terms of the rare earth element fractionation patterns for different stages and generations of calcite, as well as garnet within these same samples. So a lot of other work's been done previously by Jeff Stedman and Codes in collaboration with us. So a lot of mineral chemistry fingerprints at Ernie in terms of pyrite, epidote, and apatite. So there are distinct enrichments of cobalt and arsenic in the ore zone of apatite, of pyrite. And also in this image here on the top right, Jeff's found a nice trend that's across multiple IOCG deposits, whereby you have high cobalt and variable nickel. Epidote shows some promise with high antimony and arsenic, as well as apatite in the ore zone, which has a high manganese and arsenic again. However, for the apatite, this drops off outside the ore body. So the plot on the bottom right here shows manganese concentration and apatite with distance to ore. So you can see a lot of samples within 500 meters, but then there's a complete sparsity in the data here. There's nothing between 500 meters and 4 kilometers. So really, we want to know what happens between in this space. Does it drop off after 500 meters, 1 kilometer? Is it systematic? Is it a transition? So these are some of the answers that we're trying to answers we're trying to fill in by doing the study with multiple collaborators as well. So just finishing up to summarize. So in terms of the geochemistry, we can see that we have complex polymetallic signature of mineralization and alteration. These change with distance to the ore body. Detailed characterization and context is required for the interpretation. And we're trying to validate a lot of the mineral chemistry and fingerprints that have been found in previous studies. And we also want to target other usual suspects such as biotite, titanite, garnet, and feldspars. And again, bulk geochemistry is not enough, especially in these terrains. And we want to also apply and extend this distal footprint study to the E1 group of deposits. And that's why we'd love to have some more core in between Ernest Henry and E1. Thank you.
Thanks very much, Alkis. You are also off the hook on questions. So I will just keep going through with the order that we've got, and then I've been collating all of my questions. And fair warning to everyone, if you don't come up with questions, I will be asking questions. So maybe jump in with anything that you have. Our next presenter is Tamini, and he's going to take us from Mount Isa up across to northeast Queensland to look at some of our gold deposits and the systems associated with them. Take it away, Tamini.
Thanks, Janelle. I hope everyone can see my screen and hear me.
Absolutely.
Okay, great. Thanks a lot, Alkis. That was a great talk. And thanks, Evan, Nick, for organizing this webinar. So in today's talk, I'll be covering mainly the mineralization and alteration characteristics of intrusion-related gold deposits in northeast Queensland. These deposits hold great economic potential for Queensland, and understanding their alteration and mineralogical signatures is crucial for exploration success. So northeast Queensland hosts a wide variety of deposits, which you can see in this map. This entire area has contributed significantly to Queensland's economic growth, and from the historic gold rush of Charters Towers province to the recent exploration of rare earth elements. Today's focus will be on a particularly interesting group of subgroup, which is the vein-hosted intrusion-related gold and polymetallic mineralization. These deposits are often associated with felsic to felsic intermediate volcanic bodies. So before moving to details, I'd like to repeat the GSQ mineral system team's main objective, which is to develop an internally consistent data acquisition technique or the analytical framework. By utilizing this framework, we aim to build a comprehensive deposit characterization database, as discussed by Elena, Vlad, and Alkis in the previous talks. Our internally consistent analytical framework is compatible with many type deposits, irrespective of the location and deposit style. And we are in the process of applying this framework across Queensland. Our data acquisition starts from core scanning and moves on to multi-element geochemistry, and finally the microanalytical works that can go up to the isotopic level. Currently, our Northeast Queensland deposit characterization is at the first 2 levels of this workflow, and we are slowly transitioning towards the microanalytical territory. In today's case study, I'll explore this multi-level analytical framework and its application to deposit characterization. So we have selected Ravenswood intrusion-related gold deposit as the highlight of today's talk. It's located in the Characterisation province, which has a rich history of producing high-grade gold, and currently it remains an area of active exploration with potential for future discoveries. And this focus of today's talks is to explore the benefits of GSQ's multi-method approach to capture a wide range of data that can help us to understand alteration and mineralogical assemblages, geochemical and textural relationships, and utilize this data for high confidence geochronological study, particularly focusing the Ravenswood. So I'd like to share a brief background on Ravenswood, which has mainly 3 domains of mineralization: Buck Reef West, Sarsfield, and Nolans, where variable densities of mineralized veins are present, and these yellow lines are the superficial expression of these vein networks. And these veins are associated with intermediate plutonic rocks. So far, we have studied 4 drill holes from Ravenswood, covering our standard workflow. So we started with the typical core scanning processes, and then we moved on to multi-element geochemistry. We have analyzed 69 samples from Buck Reef, Sarsfield, and Nolans, and then we have analyzed around 16 samples in microanalytical methods. So to add a bit of our, how do we do the sampling, our sampling procedure, we start with the review of the available 3D models, sometimes shared by our industry collaborators. Existing vein networks are also considered in this sampling process. We combine high-log and Minalizer techniques with core photos. This allows us to broadly identify lithological and alteration domains for multi-element geochemistry. And our next speaker, Rhiannon, will discuss this a bit more on Northwest Queensland deposits. We also use geochemistry data donated by our industry collaborator to combine everything in our sampling procedure. So now I'll briefly share some results, starting with multi-element geochemistry. So the previous published works suggest special metal zonations in Ravenswood, which can be observed in this figure. The main theme here is the veins are hosted in a polymetallic zonation inclusion, which includes gold, bismuth, telluride, lead, copper, arsenic, and some additional metals. And it covers from Sarsfield to Buck Reef West to Nolans. Our recent multi-element geochemistry results also have comparable patterns to these, which you can see in these simple box plots. These are color-coded based on host rock, dike, veins, and alterations. We can interrogate this multi-element geochemical data in many other statistical analyses, for instance, using TSNA plots or principal component analysis. But I think we will not be able to get detailed information on the elemental association, their mineral phases, and textural distributions, because all the geochemical, these signals that get diluted in a whole rock geochemical analysis. So to obtain this information, we utilize in situ microanalytical technique, which is the 3rd stage in our current workflow. Here, we analyze some feasible gold-bearing samples using GSQ's in-house Tornado microxRF instrument. And you can see the amount of new information we can link to the multi-element geochemistry. Here in the left side, the microxRF map showing the copper and lead. These are possibly linked to the early stage of fluid movement. And the gold is associated with this bismuth. Bismuth is in purple color, gold is in like bright yellow color. And also potassic alteration is strongly visible in both of these samples in green color. So in addition to this, we identified that these visible golds has a purity of around 75%, and the rest is silver. So you can see the gold-silver coexisting phases in these heat maps, and the electrum, the gold electrum is associated with bismuth tellurium phases. So this raises further questions of what mineral phases are linked with these elemental signatures. To answer this, we need to go into the next sub-step of our analytical workflow, which is TEMA. So these TEMA mineral phase maps of gold-bearing veins from show that pilsonite, that is like a bismuth tellurium mineral phase, and possibly this is the first time reported in Ravenswood vein systems. You can also see the range of mineral phases and their textural associations for for different metallic phases, and that includes pyrite, galena, chalcopyrite, pilsonite, and numerous silicate and carbonate phases. We can also extract volume and size distribution data from these phase maps, which can be very beneficial for metallurgical purposes. So these maps are produced by GSQ collaboration work with KUT COF Lab. So now I'll move back one step in our workflow to briefly share some results on the alteration signatures. So previous works on Ravenswood alteration suggest sericite, chloride, and biotite are the main three types of alteration products. To explore this using multi-element geochemistry, I have used this simple ternary plot from GSQ study samples. Here, the main alteration trend is inclined towards aluminium-potassium range, indicating the possibility of muscovitic alteration. Our data also indicates that biotite alteration is absent in GSQ study samples. Here, we do not see a strong alteration trend towards biotite, which would require more magnesium and less aluminium, particularly for this plot. One interesting point here, the data towards the central part of this plot might indicate the presence of unaltered rocks. And we need to test it by looking at the samples itself to mark a clear alteration pathway, so that if the pathway is going towards that direction or towards the potassium direction. So to do that, on the right side of this image, you can see the sample with a relatively unaltered trend contains a large coarse vein. And the host rock here, it is affected by alteration. So this diluted signal from whole rock geochemistry can introduce biasness to the interpretation. So another important point here is this black rock alteration in this left side. Whole rock geochemistry indicates almost negligible trend towards biotite alteration. So we don't see any plots in that side of this figure. Yet the rock looks like black rock biotitic alteration. Also, high gold associated alteration, which is in this photograph, shows color variation, possibly linked to sericitic alteration. So the important point here is to note both high and low gold alteration signatures and the chemical variations are plotting within this same cluster. So now the question is, can we differentiate between these two alterations? And to explore this, we can again utilize our workflow, analyzing the samples in different microanalytical methods. So here, again, the tornado microxRF map suggests gold-associated alteration is mainly sericitic alteration, which is further affected by chloritization, which is, you can clearly see this distinct variation in these photographs. And the next one is that the black colored alteration I showed you in my previous slide, this is mainly composed of micron scale muscovite interlocked within very high volume of micron sized pyrites, which is possibly giving the black color contrast in this alteration. And also one important point to note, the amount of pyrite inclusions is a lot higher in this black rock alteration in contrast to this sericitic alteration. So this elemental and mineralogical results has significant impact on geochronology, particularly in argon-argon geochronology. The overprinted chloritization here will affect the overall thermal history of these specimens. And we can utilize these results for high confidence geochronology sampling. And I'll give a quick example in the next slide. So this photograph showing a vein with quartz, carbonate, pyrrhotite, pyrite, and minor gold from Sarsfield. And the overlaid potassium map, this gray area, is in green color and showing those sericite formed via the hydrothermal fluid movement. This locked sericite is potentially a good sample for argon-argon geochronological study, but a combination of geochronological methods can help us to pinpoint important geochronological events and geological events that can be used as like a future characterization of these vein hosted systems. And can we use a combination of different geochronological methods? I think we can, but to achieve this, first we need to identify the other datable mineral phases by using our wonderful TEMA technique, which you can see in this right side map. So I'll move on to the next slide. So using the TEMA, we can identify the mineral phases particularly interesting for a range of geochronology techniques. For instance, uranium lead, rubidium strontium, and so on. So in this BSE map, that's a backscattered electron map. And this presence of apatite in blue, pale blue dots and rutile in these red areas, we can combine these different geochronological methods to reconstruct a comprehensive geological history by utilizing this wide range of data we are producing. Now, one key question we can ask, like, how do we display this wide range of results in one place? So now I'm sharing a quick video of a 3D model showing a Ravenswood deposit from a regional to micro scale in one space. So we can zoom into the different levels of our analytical workflow, like high logger, core photograph, whole rock geochemistry, to our microanalytical techniques. For instance, now we will be able to see the XRF, Brooker Tornado XRF map of this area with different elements. And then also we can show the TEMA elemental phase maps from this interval, and which will be able to show us the combination of different phases, their textural relationships, their overall distribution. So this is a very useful tool to overview this entire data set in one place. And this model also will include up to regional scale geochemistry and geophysical data. That is really interesting. And we are aiming to release these results from Ravenswood before end of this financial year. And this is this 3D model is a collaboration work with EQ BRC Deposit Atlas project, and our industry collaboration Ravenswood Gold also donated a variety of results for this. So to summarize, GSQ's internally consistent data acquisition technique is a key for the detailed characterization of Northeast and Northwest deposits in Queensland. Our combined technique can help us to better understand mineralization and alteration signatures, which can be further utilized to high confidence geochronology studies. Also, I think the mineral scale volume and textural information is useful for metallurgical process optimization, which we can see in this figure, illustrating the wide variety of minerals with the abundance from Sarsfield quartz sulfide veins. So we are grateful to GSQ members, our external collaborators, and all of our industry collaborators. Without their active support, we'll not be able to conduct these characterization works. And I think this is a work in progress, and I believe we have a very exciting future ahead. Thank you.
Thank you so much, Tamini. That's an incredible set of data that I'm sure people will be very interested to get their hands on when it's released. We might progress through to our final talk for today, and then we'll have some question and answer for the presenters. So our final talk is Rhiannon, and she will be taking us back to Northwest Queensland, looking at characterization of the Rocklands deposit. Are you able to share your screen, Rhiannon? Looks like we might just be having a bit of a technical difficulty. Oh, good. There we go. Thank you very much.
Sorry about that. So
away.
Okay. So okay, sorry about that. So thank you, Janelle. Thank you to Nick, Nathan, and Evan for organizing. So today I'll be talking you through characterization of the Rocklands copper gold cobalt deposit in Northwest Queensland. And so this talk really builds on previous talks today and provides a case study of how our GSQ workflow was applied to characterize a deposit where relatively limited information and research has been collected. So there's many questions that we can still answer with our work. So summary, so Rocklands is one of the diverse family of IOCG deposits in the Mount Isa province. As part of our GSQ workflow, we applied hyperspectral, geochemical, and microanalytical techniques in order to characterize the alteration and mineralization signatures of Rocklands. And so a big thank you to Mount Cuthbert Group for providing the drill holes and the data, without which this study would not have been possible. So just geological setting. So Rocklands is located 15 kilometers northwest of Cloncurry, within the Maitakudi domain of the eastern Mount Isa province. And so Rocklands is hosted in Proterozoic, metasedimentary, and volcanic rocks. And so as we show on the map here, this is one of several IOCG deposits in the Mount Isa province, with other examples including Swan, Osborne, Eloise, Ernest Henry, which we heard about today, and Little Eva. So this is where the workflow becomes really important, because by doing this consistent data collection, we're able to compare the signatures of these different deposits. And so this is important with the aim to enhance understanding of the IOCG mineral system, and also to provide indicators for IOCG signatures for explorers in the region. So looking at the deposit geology, so in the map here, show examples of the structurally controlled ore bodies, which are shown in red. And so the major ones that we received data from were Las Minerales and Rockland South. And so in cross-section, we see these are steeply dipping mineralized structures, which are hosted in dolerite and sandstone siltstone host rocks. So looking at the mineralization, so mineralized zones typically are associated with veins and hydrothermal breccias. The main ore mineralogy is bornite, chalcopyrite, with pyrite, carbonate, actinolite, and magnetite. There's also supergene enrichment, which includes chalcocite and native copper. So the first two images here are from Las Minerales. So we can see this example of these amazing chaotic breccias, which have chalcopyrite, magnetite, and chalcocite class. So we get a range of different breccias. And then in the bottom image, we have example from Rocklands South. So this is really extensive carbonate with chalcopyrite and pyrite as well. So now looking at the alteration paragenesis. So we have this early albite with actinolite, and then magnetite with pyrite. And then the main ore stage contains carbonate with pyrite, actinolite, magnetite, quartz, chalcopyrite, bornite with minor K feldspar and biotite. We also see these later carbonate sulfide veins, which can cross-cut these earlier alteration assemblages, and then a final chlorite epidote stage as well. And so for our deposit characterization, so the tools that we use include hyperspectral, so 5 drill holes were scanned with HiLogger. We also did XRF, so we had continuous scanning on 2 drill holes with Mineralizer. We collected 114 samples for multi-element whole rock geochemistry. And then we look at our microanalytical imaging. So 11 samples were selected for tornado XRF mapping. And then we had 14 TEMA maps that we generated as well. And so the next step, as we've mentioned before today, so we look at the mineral chemistry, isotopes, and dating with apatite, copper sulfides, and sulfide trace element chemistry. And so this is ongoing work. And so we're really excited to get results from this soon. So this is in progress with our external collaborators. So now looking at hyperspectral mineralogy. So these are our results from HiLogger. And in this plots, we're looking at the thermal infrared. So in the top image of the screen, I show an example from Rocklands South. And so we can see we've got a range of different minerals that we can detect with the HiLogger. So this is really significant, particularly for our feldspars. As we know, in the northwest of Queensland, it can be very difficult to determine differences between albite and K feldspar, especially where they both have this reddish coloration. So the HiLogger is really valuable for us to identify these zones. And in Rocklands South, we can also see there's this very distinctive 18-meter zone of carbonate, as well as garnet and actinolite. So this really helps us to make sure that we're sampling all these different regions. In contrast, so last minerale at the bottom of the screen here, we see there's no distinctive one carbonate zone. We've got carbonate throughout the drill core, as well as actinolite, and then sort of lesser quartz as well. And so there's very rare K feldspar in this drill hole as well. So these are the sorts of comparisons that we can also make between different ore bodies as well. So now looking at our Mineralizer XRF core scanning data. So with the Mineralizer, we generated continuous scanning across the holes. So these were for 2 holes, but here I show the same example from Rocklands South. And so what we could see was that with the titanium zirconium picked out with Mineralizer, this really nicely agrees with the HiLogger results. And these broadly show these lithological groupings. So for siltstone, we have relatively low titanium zirconium. Dolerite has higher, and then the carbonate unit has basically 0 titanium and zirconium. So this is a really useful tool to help us investigate these lithological variability, which is of course important before we start to look at our whole rock geochemistry data. So now looking at the results from our whole rock geochemistry analysis at Rocklands. And so what we could see when we plot our data on this IOCG alteration discrimination diagram is that for both Rocklands South, which is shown in blue in this diagram, and last minerale in purple, the alteration associated with mineralization, which is as these filled in circles, has a dominantly calcium ion alteration signature for both Rocklands South and last minerale. And this really reflects what we see in the hand samples, with the fact that the ore-related alteration signatures are associated with carbonate and actinolite and magnetite within the main ore zone. And we do also see some of our weakly mineralized samples with less than 0.2% copper plotting towards the sodium alteration. So again, that really reflects the abundance of albite, which we could see also in the HiLogger. So all these techniques kind of complement each other and explain the signatures that we're seeing. So now we can also take this a step further and compare with some of the other IOCG deposits of the Mount Isa province. And so looking at Ernest Henry, what we can see is that this deposit has a dominantly potassium ion alteration signature, which is shown in red in that red circle. So this is quite a contrast to what we saw at Rocklands, where we have more of a calcium ion alteration signature. And so here I show we've added SWAN. So SWAN is plotting close to Rocklands, particularly for the mineralized samples. So again, with this calcium ion alteration signature. And then we also see some broader sort of plots of the different alteration signatures for SWAN, so slightly broader than what we saw for Rocklands. And so finally, we can also look at another deposit. So here we show Osborne, which is plotting towards more of a sodium rich signature. So this just highlights how with our internally consistent data sets, we can start to see comparisons between the deposits, which of course is useful for understanding the alteration signatures for different IOCG deposits and helps us to understand these in more detail. So also looking for the whole rock geochemistry, and because we're particularly interested in the cobalt associations, so what we can see is that the cobalt and the copper do have a broadly positive relationship. However, there is some decoupling, so we do see samples where we get higher cobalt but low copper. So because of this, this requires further investigation to really identify what these cobalt mineral associations are. And so as we've heard about today, we can resolve these relationships with our tornado mapping and then complement this with TEMA. So in the bottom image, we see a multi-element tornado map with sulfur, copper, and cobalt. And so the arrow points to a pyrite grain. So we can see it's got a slightly greenish color, which reflects the sulfur and the cobalt. And so using the AMIX automated mineralogy software on this tornado map, we can identify this as the pyrite grain. And then we can also see these inclusions within the pyrite grain. And so these were identified as a cobalt-rich phase. At this scale, we can't resolve exactly what the cobalt-rich phase is. And so again, this is where TEMA becomes really useful for us to determine what these cobalt mineral phases are within this pyrite. And so when we took this to TEMA, so in the bottom right image, we saw that there was linear inclusions within the pyrite. And so now another example. So in this sample, what we could see with the cobalt, so we did a tornado cobalt heat map. So that's shown in the bottom left of the screen here. And so we could see that this pyrite had high cobalt. And so again, we took this to the TEMA, and what we could see was that there was no cobalt mineral inclusions within the pyrite. So this is potentially suggesting that cobalt is instead hosted within the lattice. And this is actually consistent with the work that was done by Rosie at SMI, who found that cobalt was hosted in the pyrite in the tailings at Rocklands. So we seem to see similar results with our work on the whole rock samples from the drill cores. But this requires some further investigation. So we'll look to analyze these samples with sulfide trace element chemistry. And so finally, just some of those cobalt mineral associations, we also saw carolite, which was intergrown with bornite and chalcocite. So not only lineite, we also see carolite in Rocklands, as well as, of course, the lineite inclusions within the pyrite, and also the fact that potentially cobalt is hosted within the pyrite lattice. And so it was through this TEMA imaging that we were able to understand these kind of mineral associations. So conclusions, so high logger and mineralizer are really important tools for us to determine lithological and mineralogical variability downhole. We found that mineralized zones at Rocklands have more of a calcic ferric alteration signature, which contrasts to what we saw at Ernest Henry, which was more potassium rich. We found that cobalt was hosted in lineite and carolite, and also potentially within the pyrite lattice. So yeah, finally, just want to thank the wider GSQ Mineral Systems team, our external collaborators, and a big thank you to all of our industry collaborators who really helped to facilitate all of this work that we're doing, and a special thank you to the Mount Cuthbert group. So thank you, that is all I have. I will stop sharing my screen.
Thank you so much, Rhiannon. That's a wonderful look at the complexity of the cobalt story in the IOCG system. So we have come to the end of our talks. So I am going to kick off our Q&A session. But first, I want to thank all the presenters. It was really nice to see such a well-constructed series of talks that really showcased the workflow, but then applied it to a couple of deposits. So my first question is for yourself, Vlad. So obviously you've been involved in this process from, really the start of the project, and it generates a huge amount of data. So I was wondering if you could give us some thoughts on how you think this data could be used, should be used, and maybe where you'd like to take this program in the future.
Okay, thank you, Janelle. Well, potential uses are many, and that's why we're collecting just about anything we realistically can. The main intended purpose for external users for the exploration industry is probably for discrimination and classification if you're working in a region, and for navigation within the footprints. So for discrimination classification, to provide a really large internally consistent database which can allow you to compare any unknown samples from any place with a wide range of known ones from key deposits representing multiple mineral systems. And that should be much easier to do if you have several thousand points to compare with. And from mineralization to the footprints, that's why we're collecting so much information stepping out from mineralization. So again, it's not going to help immediately for every explorer working everywhere, but it's just provides a series of templates and useful pointers, and also it should be able to reduce the unnecessary expense on some explorers. We're doing some analysis where we're reasonably sure we're not going to get anything useful, but we need to check it anyway. And people doing their own work, they can make up their own minds where they can realistically save some money.
Vlad, it's Evan here. I've had a question come through from Greg Morrison in the Q&A. Will your data be integrated with the deposit atlas to put your data in context?
Yes, certainly, and that's the process of the deposit atlas updates. So the first pass of deposit atlas entries is putting everything which is publicly available, and for all deposits for which we're doing significant amount of work, we're doing updates. So pretty much everything we're collecting is going to appear in 3D models. It's already happening now.
We've got a question come in from Trevor Beersmore. Thank you. Keep sending your questions in. Are there any insights coming from this work regarding the origin of this class of mineral deposits that explains their variability?
Yes, probably its variability indicates, well, I presume the question is about IOCGs, and the sheer variability, mineralogical, geochemical, and isotopic, which we didn't discuss, is indicating a complex origin which cannot be linked to any single fluid and metal source. So it is probably among the most complex types of mineral systems with variable contributions of fluids and metals from magmatic, basinal, potentially metamorphic sources with any possible combination of them, and hence the variability.
We got a question from Steve Harper. Can you elaborate on the previous question with regards to the sericite and biotite alteration at Ravenswood? So from the other side of the country.
Okay, I will pass on the detailed answer to Tamini. For us, we did spend a fair bit of effort trying to actually find that biotite because we wanted to check and validate existing RNG chronology. And despite of our extensive search and lots of work done by Tamini, we couldn't. So the main conclusion here was that we don't say that biotite alteration don't exist, but proximal biotite alteration immediately in salvages of gold-bearing veins. So the vast majority of dark rock alteration we see is sericite pyrite, not biotite. Tamini, care to elaborate?
I'll just add a couple of points. Thanks a lot, Vlad. That's a great question, actually. And so the main alteration from the studied hole we have seen is sericite and very small sized muscovite, so that the muscovite crystals forms around 20 to 50 micron size, plus a lot of pyrite inclusions there. So they were intergrown. So that's why you see this black appearance in this sort of proximal small size veins. And that could be easily confused with biotitic alteration. And at the top of it, we also see chlorite alterations. So from the drill holes we have sampled, we do not see any intense biotite alteration. But probably in our upcoming sampling sessions, particularly from Nolans and Buck Reef, there could be some biotite alteration. We don't know that. But the current studies suggest very negligible amount of biotite alteration. So the main alteration pattern is, as I've said, sericitization, muscovite, and overprinted by chlorite.
We have just had a follow-up question dropped in from Greg Morrison. He says, the biotite alteration is well documented in 40 years of work and is the main ore host in the Sarsfield for the fine veinlets. The problem is really with the limited sampling done so far. So I suspect that he's suggesting that we need to do some more sampling, and I'm sure the team is very, very keen to do that if they can get their hands on the rocks.
Absolutely, and I hope we're going to be able to have a closer conversation with Ravenswood Gold people and looking at some more drill cores in a couple of weeks' time.
Yeah, so that, Nick's got a question.
I've got a question regarding the Ernest Henry sampling. So when you look at the sampling, most is in the hanging wall and footwall, and yet the stratabound nature of that with the two shear zones, I would argue that a long strike and down dip are equally, if not more so, important in terms of how you would see how similar rocks would behave as near miss indicators or even more distal. So any comments on that?
In the sampling, we're always limited to some extent by what drill cores are available to us. But with Ernest Henry, we were relatively blessed by access to a significant number of drill holes. We have probably overrepresented, well, no matter how much you do, it's never going to be enough, but relatively overrepresented sampling of middle parts of the breccia pipe. We have some samples from shallow bits, and probably where we're missing is the deepest parts, which were drilled out over the past 5 years. So I'd say in 3D, we covered it reasonably well, except the shallowest and the deepest.
Okay, cool. Excellent.
So I've got maybe a higher level question. Obviously, this is very dependent on the rocks you're getting. Is there opportunities for companies to be participating in this program? Are we still taking in samples from various deposits across the state?
Yes, emphatically yes. if we don't have representative drill cores, and in most cases when we do, and somebody offers us some more, and it's a key deposit type from anywhere in Queensland, chances are we're going to say yes. How much work we're going to do, to be able to do on that, if it's intersecting with the current work program, chances are reasonably good that we're going to do some work on that, and that's the nature of our collaboration with a large number of companies. We have done a fair bit of work on companies' drill cores. Companies seeing early results of this work, they were encouraged to donate some drill cores, and we're even doing some work on drill cores on loan. If it fits in our work program, we're going to keep it for safe storage if we can, and if we can do some work, we will.
Wonderful. So you might have all noticed that you've been promoted to panelists. This gives you an opportunity to ask a question if you would like, but you're also welcome to continue using the Q&A function. So we've got another question in about the multi-element data that we've collected. When does it get released?
It's released in batches. We started from the earliest iteration of Ernest Henry, that was back in 21. We released all the work on IOCGs we did by that time, by some time in 22, it was released in 22. More is coming, so we're just doing a fair bit of work right now. So there was a sizable release from Northwest Queensland from sediment-hosted, so-called sediment-hosted copper and lead zincs. That was a data release in 23. There is a release very much in the process of getting released. The first one from Northeast, that's Herberton District's geochemistry, and pretty much as soon as we are ready to release a package, we are. And the biggest by far release is going to happen. We're keeping aiming to do it before we get to Mount Isa workshop in August 24. That's where we need to release the bulk of the data which we collected, including multi-element geochemistry, with the exception of several drill cores which are subject of confidentiality. So just several deposits and several drill cores. There is a bit of an embargo period until early next calendar year.
So the follow-up question is, how do I find it? Which is a very good question. I believe there is a landing page for all of these various projects that sit under this umbrella, isn't there?
Yes, and so we should be updating the links to the data sets as soon as the data set is released. We'll be putting it on that landing page.
Okay. I probably can't find the landing page and do question and answer at the same time, but okay, I believe we should be able to send a link out to anyone in the webinar with the recording email. Is that right then? Yeah. Yep. So we can send that link around. This whole session is recorded, so if anyone wants to have a look at this over the next years or months, we will be sending a link around. The recordings usually take about a week to be released. We've just got to tidy it up a bit, and then it'll be available for everyone. I think that's all the questions that we have in there so far. I'm interested in knowing if the workflow applies equally well across different deposit styles. Obviously, we've applied it to a couple of different deposit styles. Is there any change to the way the workflow is implemented for different deposits, or is it really very versatile and works across deposit styles?
Absolutely variable and absolutely impossible to create a cookbook. So you're taking this number of samples at this continuous spacing, because deposit variability and deposit geometries vary greatly. And if some deposits have a spatial extent of tens to hundreds of meters through mineralization, and there we have to be sparse and use some consistent logic and spacing. For vein deposits, the entire vein could be 2 meters across. So in those cases, we are going for continuous sampling when we can, because otherwise we can't provide a statistically significant number of samples. So it's significantly variable, so principles stay the same. We're trying to collect multiple samples to characterize variability, like typical compositions and variability across the deposit. And what it looks like depends a great deal on the geometry of the deposits.
Wonderful. All right, we are nearing the end of our allotted time. So maybe just one last question, unless there's anything burning from anyone on the call. All right, I would love to know from anyone in the team, what's the most surprising thing that you found so far in these investigations? What's something that you really didn't expect that this whole process has really pulled out as something to follow up on?
I think I can answer this question, because the most surprising thing we found is the distribution of cobalt in our Mount Oxide deposit, which we are still trying to resolve the mystery. So when we have a complete story, we can do a presentation just on this mysterious, distribution of cobalt. So still in process.
Well, I can give a much more general answer. For every deposit, we have a closer look at, bring some surprises. Every single one of them. So when we do selection of deposits, we're going top down. We're going from more significant to more obscure, and every single one, which even deposits which were extensively studied by PhD students and with publications, there is always something new which either wasn't documented or different from what was documented.
Oh, we have had Alkis share a beautiful picture that you're gonna.
Yeah, this is the cobalt that Elena was talking about. So this is from Mount Oxide. We have that amazing cobalt banding that you can see around the pyrite, but we also have sort of leaching around the sulfide veins to the left of the picture as well. So yeah, we also got cobalt within the fractures of the pyrite as well. So this is something we're still trying to resolve using the team too. So just, yeah, amazing images and yeah, such insight into the samples which you would not be able to see otherwise.
Wonderful. Unless anyone else has something surprising that they'd like to share with everyone.
Well, I just want to ask for from anybody and everybody in the audience, if you have any questions, comments, please reach out and give them to us of any kind, from why do you, why don't you, to that's wonderful, to that's an absolutely waste of time. But if you say it's absolutely waste of time, feel free to elaborate, because we're continuing this work. It's still work in progress, and we are changing the way we're doing things as we go. And I'm quite happy to hear constructive feedback and any comments and suggestions, particularly from industry people, what you would find more useful in the future.
Wonderful. And one last shameless plug, a great place to have those conversations is going to be in Mount Isa in August, when we're going to have a really big data release for this work program as well. So definitely reach out to the team now, and also come along to see the wonderful work that'll be released as we go through the next few months. I am going to call that time. Our next webinar will be on secondary prospectivity in our usual time slot on the last Thursday of the month at 2:30. So please look out for the link for that one, and we will be running through a lot of the collaborative work that we've been doing with the University of Queensland in the secondary prospectivity space. it's a great work program, so please do come along and have a look at what's been going on, what new developments there are. But I want to thank everyone for their attendance. Again, thank you to the speakers for a wonderful set of talk, and thanks for coming in for the audience as well. So obviously a very enjoyable webinar. Thank you, everyone. We'll call that a day.
Okay, take care.
Thanks.
Thank you.
guys.
Thanks,
See ya.
Thanks, everyone.
See you and thank you. Bye.
Okay, all the audience is gone.
Excellent.
All the audience is gone.
Most of them. Yeah, we can. I'll look at Isa and see how we can get a few people there. Would be great.
Yep.
One thing I am interested in is some of those bulk rock compositional controls on mineral assemblages, and then driving once you know the key minerals, the element ratios in those key minerals for vectors and things like that, which would be worth, I think it'd be worth considering. By the way, the cobalt, we've done quite a bit of geometric work in the cobalt and cobalt alteration space with lineite, cobaltite, and various other horrible fine-grained cobaltian things, especially associated with lamellar black rocks and things like that. So happy to come in one day and have a chat about that. So,
Well, cobalt, that's an interesting separate story, and just about every place we go to have a closer look if cobalt is significant. It's very simple to assume, well, everybody knows that cobalt is in pyrite, and yes, a fair bit of cobalt in the pyrite, and just about everywhere about half of cobalt is not.
correct.
And hence that's a bit of a tricky business. How do you recover from it, because it occurs in multiple forms.
Yeah, exactly. Hey, why did somebody say that arsenic was in the silicates and not in the sulfides? I don't know.
I understand. Well, I think the point Alkis was trying to make is if there are sulfides, it would be in sulfides, but at some point, probably you're going to run out of sulfur before you run out of arsenic. And if that's the case, then that arsenic is going to go into silicates, and that was the story of green rock alteration of porphyry epithermals of coats from 10 years ago, and that's precisely the same thing which we see in IOCGs. So when you see some silicates which are intergrown with sulfides, quite often they have low chalcophile elements. You step out and you analyze the same silicates if they were from the same fluids, and if they don't have any sulfides around, they're enriched in those arsenics and bismuths and antimonies, depending on what's in the fluids, sometimes by orders of magnitude.
So some of those cobalt arsenic ratios are quite interesting, because obviously cobaltite. So if there's more cobalt in ppm almost, because the molecular weights are almost the same, it ends up sometimes forming cobaltite as an event with the arsenic. And so if you have late gold in an arsenic bismuth telluride sort of event, I suppose, commonly you will form cobaltite at that, and sometimes you see early lineite and other minerals, and you get secondary cobaltite as a function of using up the arsenic instead of producing arsenopyrite.
And that's why it's always going to be a tricky matter for finding consistent regular patterns across deposits, because yes, Ernest Henry has lots of arsenic, like hundreds of ppm. Some set-hosted deposits have hundreds to thousands of ppm. Some other IOCGs have 20. So there isn't much in the ore, so there wouldn't be much in any silicates out of ore. So you're not going to be able to identify your proximity to or distance from by arsenic, because there wasn't much arsenic to begin with. So you need to find something else. Same as if you don't have much arsenic to begin with, probably you're not going to be forming cobaltite, even if there is plenty of cobalt.
And it's a bit like if you have carbonates and you have sodium, you don't get albite alteration because there's no alumina in the host rocks.
Yep.
So you end.
And that's one thing. And that's one thing which we never discussed because it's a separate, more detailed conversations. That well, you have the same fluid in the same conditions, you hit different rocks, and you're going to form a different alteration assemblage.
Okay.
And how to take into account variability of the host rocks. You cannot just go by metamorphic, like metasomatic assemblage, and say, well, we know exactly which system and where we are.
Yeah.
Yep.
Exactly. Enough to keep you awake. Enough to keep you awake at night, anyway.
Well, that just keeps it interesting, and that's why every deposit you get to, and it just raises more questions than answers. And quite often, when the time is up, we know what the right questions should have been in the beginning. Yeah.
I don't know. Usually, when they're finished mining, we still don't agree on the answer.
Yep, and that's the common story, and that's a universal thing. To start doing any research, you need to have some kind of a null hypothesis to test, and just about every hypothesis testing results in the rejection of the null hypothesis, because the original assumption is always proven wrong, just to some degree.
Okay, well, with that, I will leave you with my favourite cup.
Yeah.
Same shift, different day.
Yep.
Perfect.
Okay, good.
Okay,
Thank
take
you
care,
all, persistent
everybody.
souls. Take
Hi
care.
there, Barry. Cheers.
Cheers.
Bye.
Take care.